Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. Today he's going to be looking at why we should not lose the poles' cold temperatures. Stay tuned. Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program, and he's looking at global climate change, a 2023 update. And today we're going to be looking at why we must not lose the poles, the Arctic cold. Tom, always a pleasure talking with you.
It's always great to be on here, Patrick. I really enjoy Earth is Our Home, teaching folks the basics of global climate change. We're in our third season. We're well into the 2023 season. And today I want to focus on polar temperatures, the Arctic as well as the Antarctic, and how important they are to global climate. They're incredibly important. So when people read something or see something on the news that Arctic temperatures are rising or Antarctic temperatures are rising, they may have a tendency to say, well, I'm never going to the Arctic. That's a long way from here. That has nothing to do with me. But that would be incorrect. That's false. It has a lot to do with you. And I'm going to show you what happens at the poles does not stay at the poles. The poles serve as Earth's air conditioners. If you think about planet Earth 100 million years ago, when dinosaurs were roaming what is now the northern United States and Canada, the northern United States and Canada had climates like you find now in the tropics. It was hot and humid year round. 100 million years ago. It was a hothouse Earth, about 17 to 18 degrees warmer globally than currently. In our present configuration, that is prevented, the hothouse is prevented because warm ocean water from the tropics cannot get close to the North Pole or the South Pole. Antarctica is a continent that blocks warm water flow in the south. And in the north, you've got the Arctic Ocean straddling the North Pole, but it can't warm up because Eurasia and North America and Greenland block the flow of warm tropical waters trying to get into the Arctic Ocean. They can't make it. And it's this isolation of the polar areas from warm ocean currents that produces the ice house that we're in. The ice house, 17, 18 degree Fahrenheit cooler than the hot house, is the Earth we've had. We began to go into it as far back as about 30 million years ago, but we were definitely well into it by 7 or 8 million years ago. And our genus Homo, has only been around about 2.5 million years. And upright walking apes, those first ancestors that walked upright, have only been around about 6 million years. So we and our human family, as well as all the other flora and fauna all over planet Earth, have evolved in an ice house. We are suited to living in an ice house. But the ice house is the way it is because of the polar air conditioners. And this is an exception rather than the rule in the history of planet Earth. Now, in the past, like I say, what's controlled the temperatures at the poles, whether they're warm and moderate, allowing a hothouse Earth, or whether they're cold and frozen, bringing an icehouse Earth, has depended on the positions of the continents. But now things are different. Continental drift only goes very slowly, about the rate at which your fingernails grow. So if there's anything pushing us toward a hothouse in this configuration, it's the CO2, carbon dioxide, that humans are putting into the atmosphere by burning fossil fuels, coal, oil, and natural gas. And this warming is much more rapid at the poles, especially at the North Pole, than it is anywhere else on Earth. And if we lose the poles, if we lose the North Pole, for example, if it ceases to be the air conditioner for the Northern Hemisphere, we can expect a delayed but significantly and possibly, probably catastrophic warming to follow as Earth loses its source of its cool air.
In our United States, we have 3 or 4 different tropical areas. When I say tropical areas, it's the way the climate is. For instance, in the Northeast, it tends to be cooler during the wintertime and more pleasant during the summer. But in the Western states, it's hotter during the wintertime and hotter during the summertime. So when you're talking about global climate and things of that nature, how it affects the climate, maybe it will only affect 1 or 2 parts of the United States.
No, that's really not true. I mean, even though the climate is different in, let's say, Maine than it is California, okay, yeah, their climates are completely different. But if we get to the point where we lose the poles, the climate in both places will change dramatically. Okay, it will change catastrophically. They still won't have the same climate, but it will be a much different climate from the climate in which the flora and fauna that live there now are adjusted. They're adjusted to the kind of climate we have now.
And you're saying the flora and fauna are also our crops that we grow?
Yes, that includes, yes, absolutely, crops and livestock. Yeah, whether we're talking about domesticated animals and plants or wild ones, they all rely, if they're growing outside, they rely on the temperature, the climate conditions in order to survive. Absolutely. As do humans. So what I want to show you here is how the Arctic warming is just much greater than global warming in general. We've talked on Earth as our home about global warming and how it's not uniform. Certain places warm up faster than others. The fastest rate of temperature increase in the world is the Arctic. Now, this is from 1900 to 2020. If you look at the vertical axis on the left side, that's in Fahrenheit. The one on the right side's in Celsius. I'm going to talk through the Fahrenheit one. If you look at the red, you'll see that at the beginning of the data set, the temperature in the Arctic was a little over 2.5 degrees, about 3 degrees colder than the baseline. And the baseline is at 1981, 2010 average. So looking there, it's about 3 degrees below the baseline. You follow it up, and it's now about 2 degrees above the baseline. That's a 5 degree Fahrenheit increase in temperatures in the Arctic in 120 years, 5 degrees. Whereas for the globe, the temperature in the early part of the 20th century was about a degree Fahrenheit below the baseline. And now it's about 0.8 above. That's 1.8 degree, a 1.8 degree increase in global average temperature. 1.8 degrees for the globe, 5 degrees for the Arctic. So Arctic temperatures are rising much faster than for the globe. We can't lose the poles. That's catastrophe. The Arctic warming has the capacity to generate positive feedbacks that lead to further warming. So when you melt ice and snow at the Arctic, either on the Arctic Ocean or in Greenland or Siberia, northern Canada, you melt that ice and snow, you remove a white surface, which reflects sunlight back into space and keeps the earth cool, and you uncover a blue or green ocean surface or green and brown lands, and they absorb the heat. That's a positive feedback contributing to more warming. Also, Arctic warming is responsible for releasing methane, CH4, which is in the permafrost, particularly in Siberia. And it's also in the sediments underneath the Arctic Ocean and some of those areas around the Arctic Ocean. That's another positive feedback that would accelerate the trend in warming. But the biggest impact would be of losing the Arctic. The biggest impact of a warmer Arctic would be the loss of the ability to generate very large cold air masses. Now, we know from experience, these air masses migrate south and moderate the temperatures in the temperate zones. So if you're saying Antarctica and the Arctic, they're both a long way from us, so who cares? They are Earth's air conditioners. Think cold fronts. Here is a weather map I borrowed from WBZ at New Year's in Boston. You're all used to seeing this kind of winter pattern, an Arctic blast. Look what it's done. It's pushed the jet stream down through the Dakotas, down into Arkansas, the Gulf of Mexico states, Mississippi, Alabama. And it allows very cold Arctic air to come down and give us snow and ice all the way into the central United States, all through Canada. That's a huge area that's just received a big dose of very cold Arctic air. Now, you may not like winter. You may escape this by going to Florida. But rest assured, temperatures in Florida are quite a lot cooler in January than they are in July, because some of this air seeps all the way into the tropics. This is truly Earth's air conditioner. Moreover, the flora and fauna that live in Canada and the United States, they need this kind of pattern because they've evolved in an ice house. And these pulses, these winter pulses of very strong cold fronts, Arctic blasts, are part of the climate in which all these animals and plants have evolved. Here's what happens when you get an Arctic blast in the summer. Now, actually, this was the 7th of June, technically before the official beginning of summer, but this is a summertime pattern of an Arctic blast. You see what's happened here. A big blast from the Arctic has come all the way down near the Gulf of Mexico. This is what brings us those delightful summer days when it's not hot and not humid. Here in Ohio, I would guess on a day like what we're showing on the map, it would be a sunny day with highs around maybe 70 degrees. Quite cool for that time of year. And even on down into Tennessee and Alabama and some of those places, it'd be warmer, but it wouldn't be humid. It would be a delightful day, maybe 78, 80 degrees. These pulses come in the summer, and they prevent us from having a summertime that's wall to wall hot and humid. You know, you go out in the summer and it's just unbearably hot and very humid. We would have that wall to wall from May all the way to September if it weren't for these cool fronts. And where did the air from this come from? It came from the North Pole, because a giant dome of cold air got started up there probably about 10 days before this, maybe at the end of May, and then it moved out. And it brings welcome relief to the heat we have throughout much of the northern hemisphere.
So that is in the form of the H is the cold front. Is that correct?
No, the cold front is the blue line. Look at the blue line with the arrows.
Okay. All
and
right.
the H is high pressure. Where you have high pressure, the air's sinking.
Okay.
So the air's aloft where it's quite cool, and it sinks. In low pressure, you have rising air. And you can see there's a low pressure there in Nevada. And what that tends to do is bring much needed rains to the Great Plains. We need this pattern because you see the high pressure in the central U.S., the low pressure in the West, and how it's snaking around. Look at the rains that they're getting in Idaho, Nebraska, Kansas, Oklahoma, Missouri. Those are much needed summer rains. Without those, we would not have our agriculture that we have. We wouldn't be able to feed ourselves. We wouldn't have the wheat fields out there, the corn, the hay crops, soybeans. It's this kind of weather pattern we get because of the Arctic air conditioner, which we're on the way of losing now. In the southern hemisphere, it's a little bit different because instead of an ocean straddling the pole, we have a continent straddling the pole. Now, it still blocks that warm water from the tropics from getting to the South Pole, but it does it by the land straddling the pole itself. And the land is separated from the other continents by large amounts of water in the Southern Ocean. And if you look there at those orange arrows, that's basically the Antarctic circumpolar current. The Antarctic circumpolar current is the only ocean current that circumnavigates the globe. It goes all the way around the Earth there, as you can see. And over top of it, there's the polar jet stream. That south polar jet stream blows and doesn't really have anything to serve as an obstacle. There are no land masses around there. And so it has done a lot to kind of separate Antarctica out so that the temperatures in Antarctica are not rising as fast as they are in the Arctic. Nevertheless, there is a lot of heat exchanged between Antarctica and oceans, the Atlantic Ocean, the Indian Ocean, and the Pacific Ocean. If you look at that blue going up there along the east coast of South America, for example, that's cold water kind of seeping up along there. And so it's the South Pole air conditioner, the Southern Hemisphere, I should say, air conditioner is the South Pole. And I've gone swimming in beaches, at beaches in southern Brazil. And I could tell you the water at the beaches in southern Brazil is quite cold. It's, Brazil's known for beaches, but their better beaches are a little bit further north than where you get into the southern region. Because in the southern region, the influence of Antarctica really does make those waters quite cold. Not very comfortable swimming, even in the southern hemisphere summer.
The Antarctic has land mass underneath. Is that correct?
Yes.
And the Arctic is just a major sheet of ice.
It's a sheet of ice on top of a liquid ocean. Yep. The Arctic Ocean is, H2O, whether it's liquid or ice. There's no continent at the North Pole. It's the Arctic Ocean. But the Arctic serves as the Northern Hemisphere air conditioner. And I can promise you, from having spent a lot of time down in southern Brazil, that at those beaches, even with the circumpolar current and so forth, Antarctica serves as the air conditioner for the southern hemisphere. Now, Antarctic temperatures are not rising as fast as the Arctic ones, and it's because of this circumpolar current. However, look at NASA's forecast for Antarctic warming between now and 2050. They're saying that it's going to pick up. And certain areas, it looks like it's going to be pretty significant. That dark orange that you see there in Antarctica means there's going to be quite a lot of ice melt. And so if that's the case, we're on the way to losing the Antarctic, just like we're on the way to losing the Arctic. Check this out. This will put it in context for you. Of all the places in the world, the place that's warming the most rapidly, and we showed that with the graph. Might want to go back and look at that graph. Here we're showing it with a map. The dark orange shows the most rapid warming, and that's in the Arctic. Look at all that Arctic warming. In Antarctica, you notice there's warming in that peninsula that juts out toward South America, and also some warming to the west of that area, West Antarctica. That appears to be the place where there's the most warming in Antarctica right now. Okay, so that's why we can't lose the poles. They are the Earth's air conditioner. And here are some references, readings. There's my fact sheet down at the bottom. We have the Fourth National Climate Assessment. You can Google that. It's really good to read. I enjoy reading those. I've read all four of them. I think the first one came out in 2000. Jet Propulsion Laboratory has NASA's eyes on the Earth. Christie and Spencer have generated a lot of the data that we've looked at. And there's my fact sheet. I came out with it in 2015. We've got a 2020 update. Might want to look at that.
One of the things that I found, those individuals that don't want to read scientific tomes of educational material, you'll find that Tom Blaine's Global Climate Change Update 2015, etc., is really geared for a non-scientific mind, if I can say it that way. It's easy reading.
It is written for the general public. I am in Extension Outreach. If you enjoy these videos, Earth is Our Home, I think I talk on these kind of like the way it's written in the fact sheet. I do address scientific audiences sometimes, use a little bit different rhetoric and talk a little bit different, but you got to remember I am an extension and we're about taking the university to the public. So it's written for public consumption.
Tom, you are an individual that is willing to respond to any emails or phone calls. Here on the screen is your contact information. I know that you've been getting some different questions. One of the questions I'd like for you to address maybe in the future is La Nina going away? I saw a report.
Yes, you saw that report and I saw it and everything like that. Last summer, we did a 3-part series. So in middle 2022, I encourage you to go to Earth is Our Home and read about La Nina Rules the Roost, part 1, 2, and 3, because we have been in the longest and strongest La Nina of my lifetime. And the 21st century has been dominated by La Ninas. The current La Nina is about 4 years old, and it's been very strong. It's had a big impact on Earth's climate. In, I think, early March, the news media and some other outlets came out saying La Nina is officially over. And my answer to that is not so fast, my friend. Not so fast, my friend. And that's why, Patrick, next time we're going to examine that. We're going to take a deep dive, because just like what happens at the poles doesn't stay at the poles, what happens at the equator with El Nino and La Nina doesn't stay at the equator. So if La Nina is ending, we need to know about it. And that means you need to turn into Earth is Our Home, because we're going to start dealing with that, because I'm a little skeptical on this pronouncement that it's over.
Hey, we're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program. Tom, thank you, and I look forward to our next program.
Thanks a lot, Patrick.